Let us look at proposition number 41 of book 10 of Euclid's Elements. The proposition says, if two straight lines incommensurable in square, which make the sum of the squares on them medial, and the rectangle contained by them medial, and also incommensurable with the sum of the squares on them, are added together, then the whole straight line is irrational. Let it be called the side of the sum of two medial areas. So again, we start off with two straight lines AB and BC such that AB and BC are incommensurable in square. AB square plus BC square is medial. AB by BC is medial and incommensurable with AB square plus BC square. To prove that AC is an irrational magnitude, we set out a rational straight line DE. So let's do that. Apply to DE a parallelogram DF equal to AB square plus BC square. Okay, we have applied, and let's call this G and let's call this F. So DF is equal to AB square plus BC square, and it is applied to a rational straight line DE. Again, applied to GF a parallelogram GH equal to 2 times AB by BC. Okay? And let's name this as H and K. Now, DH is equal to DF plus GH, and DF is AB square plus BC square plus GH is plus 2 times AB by BC, which means the overall DH is equal to the square on AC. Since AB square plus BC square is medial, so is DF. So DF is medial, and DF is applied to a rational straight line DE. So that means BG is rational and incommensurable with DE in length. Since AB by BC is medial, so is GH. GH is applied to GF, which is equal to DE, a rational straight line. That means GK is rational and incommensurable in length with DE. DF is incommensurable with GH. Why? Because DF is equal to AB square plus BC square. GH is equal to 2 times AB by BC, and they are incommensurable. Not this. AB square plus BC square is incommensurable with AB by BC, which means 2 times AB by BC as well. Since DF is incommensurable with GH, that means BG is incommensurable in length with GK. So BG and GK are rational straight lines commensurable in square only. BG plus GK is equal to BK, which is going to be an irrational magnitude, what we called previously as binomial. Since DE is rational and DK is irrational, DH is irrational, which means the side of the square that equals it equals DH is irrational. Since DH is equal to AC square, so the side AC is irrational. Here AC is called the side of the sum of two medial areas. So we have proved that AC is irrational. Given AB and BC such that AB and BC are incommensurable in square, AB square plus BC square is medial, and AB by BC is medial and incommensurable with AB square plus BC square. So that is proposition number 41 of book 10 of Euclid's Elements. Now in this proposition, there is a lemma, and what Euclid says is that and the aforesaid irrational lines are divided in only one way into the straight lines of which they are the sum and which produce the types in question. We will now prove after premising the following lemma. So there is as such no statement. It's basically an explanation saying that the following lemma will be used for the next few propositions, which will allow us to prove that all the different types of magnitudes that we looked at, they were all created using two lines with different properties. Now, if that line has to be divided into the original two lines, then there is only one way in which that can be formed. So that is the explanation for the following lemma. Okay, so let's see what this lemma is talking of. Set out a straight line AB, cut the line AB unequally at C and D such that AC is greater than DB. Okay, so let's cut this line into two unequal parts at 2 points. So here C cuts the line AB into two unequal parts. D cuts the line AB into two unequal parts. Bisect AB at E, which means since AC is greater than BD and CD is common to them, let's subtract CD from each. So AD is equal to AC minus CD. Similarly, BC is equal to BD minus CD, which means AD is greater than BC. AD is greater than BC. Why? Because we started off with AC is greater than BD. And from both of them, we are subtracting the same magnitude, which means the remainders will also be having the same relation. So AD is greater than BC. AE is equal to BE because E is the midpoint of AB. We bisected it. So therefore, DE is less than CE, which means E is not equidistant from D and C. Or we can also say DE is not equal to CE. Now going back to book 2, one of the propositions, it says if a line is cut into two equal parts and two unequal parts, then AC by BC plus EC square. AC by BC plus EC square is equal to EB square. Since there is another point which also cuts it into two unequal parts, we can also say AD by BD plus BE square is equal to EB square. So they both are equal to EB square. That means they are equal to each other. So AC by BC plus EC square is equal to AD by BD plus DE square. Since DE square, DE is less than CE. So which means DE square is going to be less than CE square. Now look at this equality. If DE square is less than CE square, to maintain the equality, AC by BC has to be less than AD by BD. 2 times AC by BC is also going to be less than 2 times AD by BD. Using another proposition, we know the square on AB square is equal to AC square plus BC square plus 2 times AB by BC. Only that AB square is also equal to AD square plus BD square plus 2 times AD by BD. So again, they both are equal to AB square, which means they are equal to each other. Here, 2 times AC by BC is less than this, 2 times AD by BD. So again, to maintain the equality, what should happen? AC square plus BC square has to be greater than AD square plus BD square. So, which means what the lemma is saying is that given a straight line AB, and if we cut the line AB unequally at C and D such that AC is greater than BB, then AC square plus BC square is greater than AD square plus BD square. And what are the different types of magnitudes that we are talking of? Remember, we have looked at binomial straight line, first bimedial straight line, second bimedial straight line, major, side of a rational plus a medial area, and side of the sum of two medial areas. These are the magnitudes we have seen. So next few propositions we are going to look at, given these, how do we get back the original two magnitudes? And to help us in that, this lemma is going to be important. So that is the lemma of proposition number 41 of book 10 of Euclid's Elements, along with the main proposition. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.